All right, today we're discussing identifying a liquid based on using physical properties. This is the experiment you're going to hopefully be able to conduct on your own in one of the in-person labs. And today I'm going to discuss the background information and some procedure aspects for this experiment. So the experiment consists of two parts. In the first part, you will be given a known liquid. I believe it's on page 19 where you'll find table 1 listing several organic compounds, all of which are liquids. And for each compound in that list, there will be 3 properties described. One is density, second is solubility in water and cyclohexane, and third is boiling point. So in the first part of the experiment, you will actually look at those 3 properties and determine them yourself and try to match the properties that you observe with those described on the table for the known liquid. Once you are done with the known liquid, your TA will assign an unknown liquid, which is going to be one of the liquids listed in that same table. Your job will be to conduct same 3 tests to measure density, to look at solubility of the unknown liquid in both water and cyclohexane, and finally to measure boiling point of the unknown liquid. And then looking at all 3 properties in conjunction with each other, you're going to try to identify the unknown liquid and report what you think it is. So as far as density is concerned, I'm not going to spend too much time talking about it because we have looked at density earlier in Chem 1240. I will just remind you that density of any substance is found as mass over volume. For liquids, it's measured in grams per milliliter or grams per cubic centimeter. Remember, cubic centimeters and milliliters is the same thing. One important reminder, though, that I'd like to give you here, which I even accompanied by exclamation point, is significant figure. So mass will be measured using balances, and our balances measure mass to the nearest milligram, meaning 3 digits after the decimal. In the volume, you're going to use your small graduated cylinder to measure a sample of liquid. I believe it calls for about 7 milliliters of it or so, or basically anywhere between 0 and 10, but probably in the middle, so maybe between 5 and 7 milliliters. Regardless of what volume you measure, you must make sure you measure it to proper number of sig figs, which would be 2 sig figs after the decimal, with the second digit being either 0 or 5, because of how your graduated cylinder is graduated. And so when you're dividing mass by volume and finding density, you need to then round off your answer to proper number of sig figs. What we are going to talk about in detail is solubility in 2 very different solvents, one of which is water, which of course you're familiar with, and hopefully what you know about water is that it's polar liquid. It has 3 types of intermolecular interactions, including hydrogen bonding. And the second solvent here is called cyclohexane. Its chemical formula as well as structure are shown here. So you can see it's a hydrocarbon, meaning only carbons and hydrogens are present. It is a saturated hydrocarbon, meaning there are no double bonds anywhere between any carbons. It is also fairly non-polar liquid, so in some respects it's basically exact opposite of water. Water is very polar, cyclohexane is non-polar hydrocarbon. And so the question is, how do we predict or explain solubility of certain solutes in a given solvent? And one generalization that is useful here that you need to be able to apply and be able to use it to explain and predict solubility of some substances is like dissolves like. What does this mean? Well, it means that in order to predict whether a particular solute will be soluble in a given solvent, you look for similarities. Similarities in the chemical makeup, such as structural features that may be the same, or polarity that may be similar, whenever you see similarities between potential solute and a solvent, chances are the solute will be soluble in the solvent. This, of course, is not 100% foolproof, and it's just a generalization, and sometimes you can make very logical, seemingly correct prediction unless you come to lab and check. And then you might find out that your prediction really was not working very well. So let's consider some examples. These examples that we're going to be considering, I pulled from study guide for lab quiz 2, and in that lab quiz you'll be asked to make some predictions regarding certain solvents, not necessarily solutes, excuse me, not necessarily the ones you're seeing on the screen, but somewhat similar ones. So here we have our 3 potential solutes, and here we have our 2 solvents. So water is one, cyclohexane and the other. As you can see, I left everything blank here because typically if you were here in the lab with me during introduction, I would be asking you of your opinions and your predictions, whether you think a particular solute will be soluble in a particular solvent. But because we cannot gather right now, we have to do it in this format. So the first solute here is ethyl alcohol, or most commonly known as ethanol. Here I gave you its complete chemical structure. So what I'd like you to do is take a look at the structure of ethanol and compare it to that of water. Water, of course, is H2O or HOH. And the question is, do you see anything similar in those two? And I'm not going to tell you everything because I want you to make these conclusions and understand these predictions yourself. I'll give you one fat clue though. Look at the OH group, right? So despite the fact that ethanol is an organic molecule, it does have OH group. And so what kind of chemical properties would it give to the entire molecule? I would argue polarity, and as far as intermolecular forces, I would definitely predict it having both dipole-dipole and hydrogen bonding type of forces. So hopefully that gives you enough information to sort of make an educated guess as to whether it will be soluble in water. But what about ethanol and cyclohexane? Besides having an OH group, ethanol also has this hydrocarbon portion, or tail sometimes it's called. So ethanol seems to combine in one molecule 2 different worlds, if you will. A polar group like OH and a non-polar group such as ethyl portion. And so once again, I'm challenging you to think about whether presence of this hydrocarbon portion here would possibly make it soluble in cyclohexane. Our next possible solute is hydrogen bromide, HBr. And here I picked something that is sort of on one end of polarity spectrum. So you have substances that are extremely polar, which borders with ionic, and on the other hand, on the other side, you have completely non-polar substances. So what do we have here in hydrogen bromide? Notice, by the way, the ending "ide." This ending, it's not bromine, it's bromide. What does that ending tell you? Think about that. What kind of chemical bond exists between hydrogen and bromide in HBr? I'll give you a hint again. I don't want to give out all the information. Think about the fact that hydrogen bromide is a close relative to, say, hydrogen chloride, which we know is hydrochloric acid. And we, of course, know, hopefully from your laboratory experience, that HCl is well soluble in water. So what type of bonding, again, is here? And I would guide you towards probably the fact, because it's bromide, that it is an ionic substance. So being ionic substance, would it be soluble in water? And think about things like sodium chloride, for example, or table salt. Is that soluble in water? And then finally, for HBr and cyclohexane, Are they similar in any way? Is there anything that's similar between them? With hydrogen bromide being highly polar and cyclohexane, of course, being a nonpolar hydrocarbon. Finally, a substance called 1-hexene. Of course, reminder a little bit about organic nomenclature. Hexene means 6 carbons. Ene means double bond between 2 carbons. 1-hexene means double bond between the first and the second carbon in the molecule. So I drew the structure for you. As you can see, 1-hexene is a nonpolar hydrocarbon with no possibility of either dipole-dipole or hydrogen bonding. And so this only has London dispersion forces. Considering that, do you think it will be soluble in polar water? And what about nonpolar hydrocarbons such as cyclohexane? I have been referring to hydrogen bonding a lot, so hopefully you at this point already know from lecture how to tell whether a substance will have hydrogen bonding. I would point out, and it's a very common misconception which I would very much like you to avoid, that hydrogen bonding is not something that exists within one given molecule. Instead, it's intermolecular force, meaning it's an interaction in liquid state between neighboring molecules. And in this case, this interaction in case of, say, ethanol or water, in both of which hydrogen bond is very much present, is the fact that you have partially negative oxygen and hydrogen directly attached to the oxygen. So for hydrogen bonding to exist between, again, neighboring molecules, not within one molecule, you would have to have a hydrogen directly bonded to one of 3 elements, only 3 elements in the whole periodic table. Those elements include oxygen, nitrogen, and fluorine. So if you have NH or FH or OH in the molecule, then hydrogen bond will be present. Hydrogen bond is the strongest type of intermolecular interaction, hardest to break, and substances that have hydrogen bond typically would be expected to have very high boiling points, which we will talk about in detail a little later. So now let's talk about how you're going to conduct the solubility test. You're going to take clean, dry test tubes. Medium size works well, or you can use large if you prefer. Make sure, especially when you're testing with cyclohexane as your solvent, make sure the test tubes are completely dry. Don't even wash them. Just get some clean test tubes. You're going to add some solvent to a test tube, and then you're going to add your solute, whether known or unknown, very slowly, 1 drop at a time, to see what kind of change may be occurring when 1 drop of solute is introduced into the solvent. How do you know if substance is soluble? You're adding drops of your solvent, no sign of cloudiness, meaning no change in refractive index, no sign of droplet formation on the side, sort of like oily residue on the side of the test tube. Also, as you add more, no sign of phase separation, meaning layers. You know how you have in salad dressing, for example. What would the signs of insolubility be then? Well, on the opposite here, cloudy mixture indicates insoluble substance being added. You may see oily droplets forming on the wall of the test tube, and if you shake the test tube, those droplets don't go away. Change in refractive index would, by the way, be indicated by cloudiness. And ultimate sign of insolubility, of course, is when you added enough layers form, so one liquid basically separates from the other, sort of like oil and vinegar in the salad dressing. I would point out that in nature things are pretty much never black and white, and so you may have a situation where solute may be slightly soluble in a particular solvent. What does that mean? Well, it means first 2 to 3, maybe 4 drops will go in with no change obvious, but then As you continue adding that solute, you start seeing either cloudiness or layers or both. So be cognizant of that. In the next video, we'll be discussing measurement of boiling point and what factors affect its magnitude.